Good morning, students. Today we are going to discuss a few important topics from chapter 10, Mechanical Properties of Fluid. The topic which we are going to discuss, relation between surface tension and surface energy. So already we have defined these two terms in our last class, surface tension and surface energy. Now today we are going to try to relate these two parameters. Now for that, let me draw this diagram. Let me to explain this diagram. Now you see, you do have a frame. Frame is made of wire, and it is in the shape of U, alphabetic U, and over the arm there is a slider AB. Now what you have to do, you have to insert this frame in soap solution. So what happened basically, if you dip this frame in soap solution, a film will be created, or you can say film will be there in the arm, or you can say in the boundary ABCD. So the film is there, ABCD, soap film. Now what it will do, as per the definition of the surface tension, it will try to minimize this area. Now to minimize the area, the film pull the boundary. Now it will pull CB, it will pull AB, it will pull AD, it will pull CD, and that one we have defined by capital T. Now as per the definition, tension always tries to minimize the area. Now what is our job? Our job is to increase the area, and for that what we will do, as all the frames are, or all the wires are fixed except the wire AB. So what we will do, we will pull the wire AB to A dash B dash, so that the film will or the area of the film will increase. Now as per the definition of work done, if we pull the wire AB by a distance delta x, then the work done will be your W equal to F delta x. Now if we go for the definition of surface tension, the formula for surface tension is your T equal to F by L, that is your force per unit length. Now what we will do, we will substitute F from 2 in 1. So if we substitute F from 2 in 1, it becomes easier TL delta x, TL delta x. But we have used that alphabet 2 times. What's the meaning of giving 2? Actually, you see, film is, you see, whenever there is a film, it has two surface area. Now how can we define surface area, number of surface area? You see, it define the contact with the air. So if you consider a film, inside the film there is an air, and outside the film also there is an air. So as it in contact with the air, internally as well as externally, that's why we are considering the numerical value 2. It has two film or two surface area. Now if you consider bubble, if you consider drop, film is nothing but some kind of bubble, is not it? Now if you consider a drop, you see inside the drop there is a liquid, but outside the drop it has only contact with the air, so it has one surface area. Now film has internally empty as well as external. So internal there is an air, and externally is also there is an air. As the two surfaces are in contact with the air, that's why number of surface is 2. So you see, as it is film, so it has two surfaces, so W equal to, and two surfaces means surface tension will be twice. So that's why whenever there is a term surface tension, we have to see the number of surfaces. As per the number of surfaces increases, so tensional force also increases. So W equal to 2TL delta x. This work done is equal to the potential energy of the liquid film. So for the energy wasted for doing work gets stored on the film as its potential energy. Now increase in area of the film, if you consider, definitely as it has a two surfaces, so increase in area is also V2 times 2L delta x. Now surface energy is nothing but is your potential energy by increase in area as per the definition of surface energy. So potential energy is your 2TL delta x, and the increase in area is your 2L delta x. So if we cancel it out, it becomes only capital T, and T is nothing but is your surface tension. So this proof that surface energy is nothing but is your surface tension. So sometime in numerical we are going to use this equation, surface energy is equal to surface tension. So the relation between surface tension and surface energy is your what? It has numerically equal. Okay, so please check it out. Now next topic which we are going to define, that's your angle of contact. Now this parameter is very important in our last topic which we are going to discuss in our last class, that is means next class. Now let me define. Now you see, if we already have defined in our previous class, surface tension always tries to minimize the surface area, no? Or yeah, free surface gets pulled downward, you can say, due to the surface tension. Now free surface always gets pulled towards downward, but the liquid which is in contact with the wall, it has different forces. So based on the magnitude of the forces in the middle portion of the free surface, as well as forces at the wall of the container, the shape of the free surface sometimes concave, sometimes convex. So if you consider water, the liquid surface, free surface is concave, but if you consider mercury, you will see that it is convex. So as per the definition of angle of contact, you see what you have to do, you have to draw a tangent, and the angle made by the tangent with the solid surface inside the liquid is nothing but is your angle of contact. So the surface which are concave, the angle of contact is your acute, but the surface which is convex, the angle of contact is your obtuse. So let me define the angle which the tangent to the liquid surface at the point of contact makes with the solid surface inside the liquid is called angle of contact. So whenever you draw tangent on the curved surface, you have to find out the angle made by the tangent with the solid surface inside the liquid. Solid surface inside the liquid, that's very important point. And the angle is nothing but is your angle of contact. Now next topic which we are going to define, excess pressure inside a liquid drop. Now already you have said drop has only one surface, is not it, because inside the drop the liquid is there, but outside it is contact with the air. So number of surfaces contact with the air can be defined the number of surfaces. If 2 times it is in contact with the air, then 2 surface. If it 1 time it is contact with the air, is 1 surface. So you see, you do have a liquid drop of radius small r. So internally there is a pressure P, and externally there is a pressure P suffix A. A is for atmospheric pressure we are considering. So what will happen? Excess pressure means what? Internal must be more than the external, is not it? And then what will happen? The bubble will, or the drop will expand. Here we are considering drop, so drop will expand. So outward force is nothing but is your excess pressure, that is P minus PA, that is your excess pressure, and area is your 4 pi r square as it is in spherical. Now work done for expansion by the radius dr is nothing but is your P minus PA 4 pi r square dr. So increase in potential energy. So increase in potential energy, we have to use this parameter. So surface energy into increase in area, and surface energy is nothing but the surface tension. So increase in potential energy is nothing but is your tension into increase in area. So you see, tension T and increase in area is your 4 pi r plus dr whole square minus r square, as you have taken 4 pi outside the third bracket. So on expansion, r square plus 2r dr plus dr square minus r square. On simplification, r square and minus r square goes off. Dr square can be neglected because dr is very small. So only left 2r dr. So increase in potential energy is nothing but T 4 pi 2r dr. Now this potential energy and work done, they have numerically equal. So P minus PA 4 pi r square dr, T 4 pi 2r dr. So what happened basically, this part cancel out, 4 pi goes off, 1 r goes off. So ultimately we will get P minus PA equal to 2T by r, and r is the radius of the drop. So you see excess pressure is nothing but 2T by small r. Similarly, if you go for the bubble, what you have to do, you have to multiply 2 in the equation 3, because surface tension term is related. So if you multiply that equation by 2 and if you simplify, you will see that the expression comes out to be your P minus PA 4T by R. So I am leaving on you, please check it out. 1 and 2 will remain same, only 3 will be 2 times. So because surface tension T is there, so whenever tension term is there, you have to count the number of surfaces. So in case of bubble, 2 surfaces, so on simplification you will get P minus P 4T by R. So excess pressure inside the liquid bubble is 4T by small r. So I am leaving on you, try this one, it's very simple. Now next we are going for the application part for the excess pressure. The excess pressure inside a soap bubble of 2 centimeter diameter is 4 Newton per meter square. Find the surface tension of the soap bubble. So P minus PA is your excess pressure, that's given 4 Newton per meter square, and diameter is a 2 centimeter, so radius equal to R equal to D by 2, so it comes out to 1 centimeter 10 to the minus 2 meter. So use the formula P minus PA 4T by R. P minus PA 4T by R. P minus PA is your 4. 4T by R is your 10 to the minus 2. So 4 goes off. So T equal to 10 to the minus 2 Newton per meter. So tension is a force per unit length. So unit is a Newton per meter. So please go through this part and try to make your note. And try to go through the topic. This part is very important for exam point of view. Thank you.